to a great session. Okay, so we're recording. Terrific.
I was just reminded that.
Yeah, good. So, so I just wanted to maybe to say just a very few words about what I saw yesterday, and maybe it'll resonate with some of you, and maybe not. But I mean, first of all, it was really a great cross section of what's going on, and I was super impressed with the steps, the leaps that have been made in what I'll call sort of infrastructure for doing this kind of autonomous discovery. You know, like the solid state inorganic compound search system that Gerd Ceder's group has built and is launching. And I had a little sidebar chat with Jan, and she said they've just already discovered a few tens of new compounds. So that sounds terrific for the future. You know, I was really quite interested in the framing that Simon put out there about you know, sort of we're in the age of prospecting, and that was then again echoed, I think, through a couple of the talks, and I was really excited when Taro's talk came up, because he broke the process into sort of two categories, right? One we called optimization, and the other was you know, discovery or something along those lines. And that just hit immediately, because that's kind of the way I've been thinking about it as an observer and not a doer in this area of autonomous discovery. And you know, the feeling that I have is that, you know, we're a long way on the optimization pathway, and there's lots of great tools that are being built in this way. And you know, next steps could be turning what happened yesterday with his type 1 and type 2 behaviors for electrolytes and electrodes, what I'd call sort of a serendipitous autonomy or automated serendipity. You know, it'd be great the next step if you know, some AI that was watching the whole process would have said, oh, we see a coal plot that looks like an electrode, you should pay attention to that. So that would be kind of the next way of thinking about you know, bridging from optimization towards discovery, and from serendipity to control. I mean, I do think that, you know, for me, and it's easy for me to say this because I don't have to do the work, you know, the exciting future for this whole autonomous discovery is really that word discovery, and going beyond you know, sort of optimization strategies, which become very sophisticated and very effective, and thinking about how we step outside of the bounds of the box that we're trying to optimize over, and recognize not just the you know, that's, you know, a eureka kind of moment, but that's interesting or that's curious kind of moment, which is, you know, what a scientist does in the laboratory. We're probably a long way from that, but I think that, you know, in my mind, that should be kind of where we're aspiring to, is being able to capture rare events and decide whether or not it's a cosmic ray hitting the detector, or if it's really a new peak that says we have new physics or new chemistry going on here. So I also think that, and I think we'll hear more about that this afternoon, more things about in situ experimentation, where rather than just trying to map out a big phase space, we're actually trying to study processes or study mechanisms of you know, how materials grow or how they nucleate, and how phases compete, because ultimately this is the kind of thing that will give us insights into, you know, how building blocks of matter assemble, or what the mechanistic rules are that will take us outside the box that we're studying and look at other phase spaces, you know, sort of generate that kind of intellectual capacity. So anyway, I will stop. I'll get off my soapbox here right now and see what Ute may have to say more specifically about synchrotron stuff. But I was super happy to see the way things are going, and the sort of thought processes are sort of congealing around in different directions, and people are actually, you know, taking those steps that are necessary. We have a long way to go. I mean, I think it was Simon or somebody, you know, talked about this hype curve, and you know, we're kind of going up the hype curve, but I think maybe call it a hype curve, called a possibilities curve. And you know, we're trying to explore ourselves what those possibilities might be, and it's going to be a research project in itself to understand how to do research autonomously. So, Ute, that's all I had to say. Any thoughts?
Yes. So I mean, we discussed a little bit with Taro's point, like looking for electrolyte and discovery a new electrode. This was also something that was for me very interesting because we are accelerating science so much with the autonomous approach that in principle you can also spend against the resources on probe too much. So you're not just aiming for your question to be answered, but you can also check for other properties, which might not be something you're looking for directly, but because you get it more or less for free, you can just check out like if there are other properties matching. So even if you look for electrolyte, maybe you find a great electrode material. So it was something I liked. I liked also with Taro's talk, something that's closer to the heart here of user facilities. And so there's always this challenge of standardization of data formats. And I am impressed about 2 points here. First of all, Japan is going for a data standardization, but also that this is triggered by industry. It's not triggered by science, which is also very interesting to observe. So I'm very curious how this is developing and if it might be also for us a good idea, like to join to use it if it's really proving to be easily to apply. And coming back to synchrotron experiments, I also would love to see more like the boundaries, caveats, and opportunities, how to also find opportunities to merge autonomous experiments with synchrotron. Because for many, first of all, it's like a clash of cultures, right? But it doesn't have to be. And how to make it possible that this becomes applicable, that we can also maybe offer something directly at the beamlines to go to the cutting edge. It would be very interesting to me to see like what is really needed, and also where are the situations where we have to pay attention? Where do we have to maybe develop more tools to be sure that we can also do the quality assurance of data? So I think that's something bringing us already to the point here, what we want to discuss today. And maybe we can go ahead and start with the first speakers here. And in this afternoon, the pleasure of being the first one is Karina Chapman. I hope she can reply to many of my questions here already and join into it as somebody who has worked at a facility for many, many, many years. So really a child of the synchrotron, and now being a professor at Stony Brook to share her insights, like where she also sees the opportunity field here.
Wow, this is said it's loading really slow.
Yes, I'm sorry. Yes, that looks good.
Okay. Okay.
Thank you.
I'm not sure if I'm going to get all your questions, but I think I'll hopefully leave lots of room at the end so we can have a discussion for whatever I've missed. So today I'm going to be talking about some of the challenges and some of the approaches that we've been working with to try and use in situ synthesis studies, mostly using synchrotrons, to help with materials discovery. And for us, the underlying motivation for this is that every revolution in energy storage or solar energy conversion has been driven by the discovery of a new material. And so computational materials scientists can predict what these materials are going to be. They can draw it out on paper, you know, the composition, this material, and they can calculate the properties and say, this is what you should make. This is what's going to make our next best battery. But what's holding us back from being able to do that and hold it in our hand and actually test the properties and put it towards use is the fact that we can't predict how to do that synthesis. So at least for inorganic crystalline materials. So my organic chemistry colleagues can draw out a molecule on a piece of paper and they can sketch out the reactions that will get them to that product. We can't do that in inorganic chemistry to make new materials. And so we're stuck in this Edisonian loop where we choose reactions, we choose conditions, we run a reaction, we recover it. Did we get the right thing? Yes, no, mostly no. and we go around this merry-go-round until we end up with something useful. And so if you've been doing this type of synthesis for a while, you'll be more successful because you'll be guided by intuition and your experience. And so that's just probably a way of saying that there's fundamental science that's underlying this process. So we should be able to predict it. We just haven't codified that underlying science yet, and we don't understand the mechanisms fully yet. And so this is where, and part of the reasons why this is difficult, and difficult when we're talking about inorganic synthesis, is because we're looking at a couple of phenomena in chemistry and structure and energetics and the mobility of species that couple across multiple length scales. So atomic scale, we have processes that happen at interfaces, we have particles that maybe break down and reform, and we have different constructions on the reaction level. So this is 7 orders of magnitude where we have those couple transformations. So understanding what's the important phenomena that's governing a reaction could be happening anywhere across those length scales. So that's from anywhere from me to the moon. That's 7 orders of length scale. And so it's a really challenging processes to understand. But of course, we have synchrotron tools and in situ tools that can allow us to probe reactions on those different length scale with chemical and structural sensitivity. And so that's what we do, in the same way that you can, probe operating systems with X-rays to see why they work and maybe why they eventually fail. We can also use X-rays to understand the reactions and the mechanisms that lead to the formation of the materials themselves. So we can start to build up this working knowledge of how materials form, and ultimately so we can predict the pathway to these new materials. And so this is a lot of work that we've done as a focus of the Genesis EFRC. So it's our next generation synthesis center that's based here at Stony Brook. And our goal is to be able to use in situ tools to understand the mechanisms that are governing synthesis reactions, ideally, ultimately integrate that with some real-time analysis. And once we've identified the synthetic controls, the handles that are important to governing the outcome of a given synthesis, be able to tune that towards our new material. So that's the overarching goal. What are some of the challenges that we face and that we've discovered in doing this? So, challenge 1. Nucleation is a nanoscale phenomenon. So if we're trying to understand the point of differentiation between one product or the other, we need to understand structure and how it's forming on the nanoscale. And of course, as we're reducing materials to the nanoscale, we have small particles, we have very broad Bragg peaks. So we're not able to use Bragg diffraction to characterize how this process is going. And so this is where we come in and use the pair distribution function method, which is giving us atomic scale, detailed atomic scale information, but for nanomaterials. And of course, many of you will be familiar with this, but we can pull out information about the atomic positions. The coordination number is coming out from the peak areas. We're getting information about particle size, and we can apply structural models to all of these. And so we can do PDF measurements using the high energy synchrotron X-rays on an appropriate timescale to start to look at reactions of solids, so solid gas type reactions. So we can collect data routinely on the order of 1 second or sub-second timescales in order to follow reactions. And so here we are. This is one of the earliest reactions that we were able to watch, looking at nanoparticles form, supporting on a solid area support. And we can initiate the reaction by switching from an inert gas to a reducing gas, which then initiates the reduction of platinum 4 to platinum 0, and we start to form nanoparticles on the surface of titanium, which, if we subtract off the contribution from that titanium support, which doesn't change through the reaction, we can see beautiful peaks that grow in from the platinum as we're forming it, to understand the kinetics and the mechanism for this formation. So we can go through, quantify the data, pull out peak areas to look at the concentration of those different atom-atom correlations. And the key thing that we can get out of this, we realized we could get out of this, was we can see big jumps in the platinum coordination number, which corresponds to, well, an increase in the concentration of platinum-platinum distances. But of course, we haven't reduced any extra platinum. So it's a fairly uniform reduction of the platinum. And so what this is telling us is these are points at which, temperatures at which the mobility of the platinum on our surface is increasing. And all of a sudden, those small clusters which are isolated can aggregate together and form larger particles with higher average coordination number. And so synthetically, the feedback that this gives us is that in this system, the mobility of the platinum changes at about 135. And if we want to retain our small catalytic nanoparticles, we need to keep this reaction below 135. So we've been able to do this type of study. We're looking at solid gas reactions on suitable timescales for quite some time now. So the challenge then becomes, how do we look at these processes when we have we need fast time resolution? So if we have systems like reactions that are happening in solution, they're not constrained by the mobility on the surface, and there's much faster restructuring and dynamics of the solution phase reactions. So how can we start to look at a process where maybe we need to acquire data for much longer, maybe a second, maybe a minute, but if the structure is changing on the order of sub-seconds, then what we will end up looking at is going to be a superposition of all the different states within the reaction at that time. And so if we're trying to ask ourselves, when the horse is galloping, is there a point where all the legs are off the ground at the same time? We can't answer a question like that about a reaction. And so to address this type of challenge of these faster time resolution reactions, we were able to take advantage of the property of solution reactions that they flow. And we can then spread our reaction out in space by flowing our reactions, mixing two reagents, initiating that reaction, and then continuing to flow that reaction mixture or that reacting solution along some kind of flow capillary. And what that means is if we put the X-ray beam just next to that initiation point, that's telling us about the early stage of the reaction. And we can sit there for as long as we need to accumulate data for a quantitative analysis. And then if we want to look at a later point of the reaction, we can translate. We look at a later point along the flow path. That's a later point of the reaction. We can accumulate sufficient data to do a quantitative analysis. And so the initial test case system that we looked at to test out this approach was to look at a mechanoite, the formation of mechanoite, which is an iron sulfide, a layered iron sulfide structure with tetrahedral iron sulfurs that are edge sharing. And people have described the formation of some kind of amorphous or nanoscale intermediate in the formation of mechanoite, but obviously they weren't able to characterize it and capture it before it was transformed to mechanoite. So we did this type of reaction. So my student Michelle developed a reactor where she mixed the two different reagents together and then allowed the reacting solution to continue to flow along the capillary, and then was able to take data suitable for PDF analysis at multiple points along that flow path. So multiple points corresponding to maybe 5 data points in the first second. And then accumulating data there for several minutes, she was able to get PDF of this first intermediate, which it turns out looks nothing like mechanoite. Well, actually, it does look something like mechanoite, but it's definitely not mechanoite. But it's got a very similar local structure. So you still see that you have the same iron sulfur distance, the same sulfur distance. So you've got iron sulfur tetrahedra, but we don't have the long range structure of mechanoite. And after testing various different structural models, what Michelle was able to figure out is that early in this reaction, what she's forming is just single isolated nanosheets of this iron sulfur product, which then ultimately, eventually stacks together to form that mechanoite structure. So this would be the amorphous or the nanoscale intermediate that people had previously identified. And of course, this is interesting if you're wanting to understand the synthesis of mechanoite, but sort of more interesting for us is that it tells us that this is actually a building block that we can think about using for our reactions. And maybe not to form mechanoite, which we know we can make, but we can think about, if we have this building block or a synthon, we can start to think about how can we assemble it in different ways, how can we intervene in this reaction and maybe redirect it and form some kind of different layered heterostructure where we incorporate something else, different layers of different composition. Yeah. So this is an approach that we took because we had very fast restructuring in solution. Thinking about the other case, we can also have time limitations. So if we have very slow reactions with slow kinetics like you typically see in solid state reaction, how can we efficiently map out that kind of reaction space? And how can we possibly hope to do it within the limited 2 days beam time that we've been allocated for our synchrotron measurements? And so part of the reason that solid state reactions are slow is because, well, you start off with your precursors and they have your different components. You're building chemical building blocks in 2 different components. And you have to have all those atoms move and rearrange entirely to form your product. So you have to change the composition. So this is a transport limited process because you're doing it, transport is limited in the solid state. And so typical approach that chemists will take to accelerate these types of solid state reactions is just to heat it up. Go to higher temperature, transport is faster, so the reaction goes faster. So we can start to map more of the reaction space. But of course, there's a trade-off here. As we start to go to higher reaction temperatures, we start to favor the thermodynamic product. And maybe all the interesting things that we're interested in might be metastable phases. So how can we access this rich variety of metastable phases? So clearly it's a balancing act of figuring out what the ideal temperature is to get the reaction to go, but to still retain the stability of that metastable product. And if we're doing this iteratively in the oven and then taking out a sample to look at, it's going to be a long time. Each cycle is going to take us quite a long time to figure out, did we get the right thing and dial in the right temperature. So of course, we've been able to use in situ reactors to look at these types of reactions as they're happening. So looking while we're cooking with the synchrotron beam or an in-house diffractometer in order to map out that reaction progress and get a lot of feedback. So this is an in situ reactor that I think maybe quite a few people will have used, where we can heat the sample also under controlled gas flow. We have a thermocouple right next to the sample that's giving feedback of the temperature, and we have a wire wound heater that that's heating the sample. And so this allows us to look at a lot of reactions, but of course we can only look at one temperature at a time. And if we start to say, hey, we want to find the right temperature for a metastable phase, we really want to be able to map that important phase space and all the different temperatures as efficiently as possible. And so one approach that we've been taking is to parallelize this approach. So instead of just looking at one temperature at a time and looking at the same reaction for 3 hours, 12 hours, as long as it takes for that reaction to progress, we can start to consider looking at multiple temperatures in parallel by generating a thermal gradient across the sample. So one side of the sample could be sitting here at 350 degrees, and the other side of the sample could be sitting at 150 degrees. And by moving the sample in the X-ray beam, we can look at different temperature points and look at it as a function of time. And so we can monitor the reaction progress as a function of time at multiple temperatures in parallel by using a thermal gradient. And so this allows us now to more efficiently do variable temperature reactions. So of course we can look at a whole bunch of temperatures in parallel without worrying about the overhead for heating and stabilizing that temperature. We can do things ex situ ahead of time or just screen a lot of different reactions. So we can heat in this gradient, recover the sample, and then map across the sample to see what the products are and to dial in exactly what that temperature is. We might want to set our oven to look at a bulk sample. And we can also map out the kinetics of different reactions at different temperatures. And ideally, with the goal of being able to identify, that particular time and temperature regime that's going to give us those particular metastable phases. So in doing this brings us to challenge 4 in figuring out what are the actual important parameters that we need to be controlling for our synthesis. And this is an important question. So when we're looking at these solid state synthesis reaction, there's a lot going on. We have to break bonds in our precursors. We have to make bonds in our product, and we have to move everything. So we were asking ourselves a question, can we just understand the importance of those transport limitation and how that governs the reaction? And so the systems that we chose to look at the transport effects, or to try and isolate the transport effects, was looking at an ion exchange reaction, where we're only exchanging the ions and we're leaving the two matrices that they're moving between largely untouched. Obviously, that's just a first approximation. And so the example that we looked at here was a rock salt, lithium salt, exchanging with a layered transition metal oxide phase. So exchanging the lithium for the sodium in this phase. And so for the first approximation, those matrices are staying the same. And so we're just looking at the role of the movement of lithium and sodium with respect to each other in governing this reaction. So we can look at these reaction kinetics. Now we're looking at a single temperature. And even though we expect solid state reactions to be slow, we were surprised to see that actually we're getting a lot of reaction happening most of the reaction was happening in the first 60 seconds. So very fast initial kinetic behavior, and some complex kinetics behind here where it's definitely nonlinear. And if we change a little bit how we do this reaction, we see a big difference in the amount of product. So we go from having maybe 14% product after 10 minutes to having 35%, so more than double. And so the question is, well, what did we change here that had this big impact on the amount of product? And so, well, normally when we think of increasing the amount of product, we're thinking about increasing our temperature, but this is not what we did here. Actually, what we did here was really simply, we take those same reagents and we smushed them together. So we increased the contact area between our two reagents. So effectively, we decreased the transport pathways for that reaction. And so another way of looking at that is we can look at the two different packings and we can say, well, when we smushed our reagents together, then most of our particles were next to a particle that it could react with. But when we had the lower density packing, and that would be this case, this 25% packing case, this is typical of what if we just took that powder and we put it in a capillary, like we were preparing a normal powder diffraction sample. If we just had that lower packing case, then actually about half of our particles were not actually sitting next to a particle that it would react with. It was sitting next to a particle that was like itself. And so this says that this is actually a pretty important effect in governing how much reactivity we see, if any. So this microstructure effect, or this architecture, is more important than the temperature in governing this particular reaction, which is limited by transport. So something that we perhaps hadn't codified before during this experiment. Okay, so challenge 4, and I know Uta brought this up yesterday, is how do we harness multimodal measurements? And so we talked about how these synthesis processes involve a coupling of chemistry and structure and changes in energetics and multiple length scale, and probably more than we can understand with any one single experiment. But of course, we have opportunities to combine different complementary tools that allow us to probe different parts of the experiment, or different parts of the reaction at the same time, to help us tease apart the coupling and the causal relationships between these. And so there are many different tools that you can think of combining. The one that we started doing, and this is work that we started quite a long time ago, was combining drifts IR with X-ray scattering. So this is something that we can do without compromising either measurement. And so the X-ray scattering is dominated by the high Z species in the material, and the IR is giving us sensitive information to molecular speciation. So it's telling us about water or OH groups that might exist on the surface of our sample that we can't see with our X-ray measurements. And so we went ahead and we developed this capability, and we're able to do these type of combined drifts, IR, X-ray scattering measurements. And the systems that we were looking at, the systems that we were looking at quite a while back, was looking at the formation of silver on a zeolite support. And so this was work that was done by a postdoc, Haiyan Zhao, who is now an associate professor at Idaho State University. So it tells you just how long ago it was that we were looking at this. And part of the reason that it took us so long to pull together this story was figuring out how to get the most out of this multimodal experiment. So forming silver on our LTA zeolite, there are two routes. We can either reduce it chemically under hydrogen gas flow, or we can just heat it and it undergoes an auto reduction. So two different reactive steps that we explored, and we can collect X-ray scattering data for each route, the complementary PDF that we derive from that X-ray scattering data. We also have the drifts. And so maybe 8 years later, we finally figured out how to analyze this data and pull out new structural information. So we have these different types of complementary data. Just to orient you, if we look at the PDF, what we actually see is we have our silvers sitting in the 6 ring. We see the silver move into the center of the 6 ring in some kind of intermediate state. Eventually, the silver forms small clusters that are confined by a zeolite. So these are about maybe 8 angstrom clusters. And eventually they grow to large nanoparticles, which must be sitting on the surface of the zeolite. So we can see this in our X-ray scattering data. We see small angle scattering that's telling us about the particles we're forming. We can see shifts in the lattice parameter of our zeolite. We can see the formation of the crystalline silver on the external surface. We have our drifts data that's telling us about the hydroxyl group and the water species that are in the pores during this reaction. And we can quantify every one of these pieces of data. We can quantify everything's going on here and still not understand this bigger picture. So lots of data here. And what we realized is we could then take this data and simplify it by using a non-negative matrix factorization, which takes all these conventional analyses and then refactorizes it in terms of a basis set that represents the distinct states within the sample. So we could take all the trends in PDF and XRD and drifts IR, and we could apply an NMF analysis to simplify it. And what it basically tells us is there are 5 distinct states of the sample that can be described in terms of their different PDF or the different infrared signals. And these are what are changing together. And so we can describe these different states of the system, pulling together all these distinct types of data. What this doesn't tell us is what caused what. And how do we figure out which particular change is responsible for the changes that we see. And so what we realized, if we want to start to compare the data and compare things that are happening that we see in the data, we need some kind of technique agnostic approach. And so what we realized we could do is we could do a correlation analysis. So this is a Pearson correlation analysis that just gauges the similarity of every PDF data set with respect to every other one and shows it how similar it is. So it shows you here, there are basically, in this case, sort of 3 states of the reaction. And we can do this for each type of data that we have. And we can get this kind of Pearson map. And then we can go and take a differential of this to then pull out the temperature at which we start to see changes in that type of data. So the onset of the structural transition. And so when we do that for all the distinct different types of data, what then pops out is, regardless of which, whether we're using the reduction route or just heating it in an inert environment, we can always see the transformation starts in the IR a little bit earlier than what you see it in the PDF, and that's a little bit earlier than what you see it in the XRD. So really what this is telling us is the changes in chemistry, so that's the water speciation on the surface of the zeolite, happens before you start to see changes in that silver moving around, which is what you're sensitive locally in the PDF. And that happens before you have a coupled correlated long-range change, which is what you're sensitive to the XRD. So really the control parameter here is what is happening in the IR. It's the change in the water and the removal of water from the system. Okay. So then the final challenge is where we're moving towards here. Once we can control things, once we can identify what are the control knobs that we need to do, is how do we steer reactions autonomously towards targeted outcomes? And I know Simon in his presentation yesterday talked about this. So this was just our goal was to try and figure out how we can do an autonomous measurement. And the system that we chose to look at was copper supported on gamma alumina. So it's very similar to that platinum example that I showed first up, where we can change the copper oxidation state by changing the gas mixture that's flowing over the sample from oxidizing to reducing. And we can probe the state using Zane spectroscopy. And so we set up to do these experiments at 9 p.m. This was the last experiment that we did before we were locked out for the pandemic. So this is work done by Daniel and Yevgeny in Simon's group. And so what they did was they wrote an algorithm that did a linear combination fitting to the Zane's data as it was collected, which figured out the average oxidation state and then either increase the amount of oxidizing gas or increase the amount of reducing gas in order to steer towards the target oxidation state of copper 1+. And the good news was it worked. We got to somewhere close to copper 1 after a couple of steps in this case. And so obviously there's a long way to go in implementing these types of autonomous reactions. In terms of the chemistry, what this means is we can start to target particular oxidation states, which means certain vacancy concentrations or oxidation, oxygen vacancy concentrations. And it allows us to target states that we couldn't straightforwardly consider controlling with a single parameter. So instead of iteratively going backwards, forwards and doing multiple reactions, we can start to think of just putting one set of reagents in and steering, once we know the right knobs, towards the right reaction. So just to summarize, these in situ measurements allow us to understand the structure and reactivity. By designing new reactors, it allows us to understand either different conditions or phenomena or timescales, which may be widely varied depending on the chemistry of the systems that we're interested in. These phenomena can cover multiple length scales. And so the solution case is pretty easy because we're just dealing with ions as they assemble. But as we start to get towards solid state, things get much more complex and we're dealing with large particle sizes and assemblies and aggregates of reacting particles. We need to think about each of these length scales in order to understand and deconvolute why a reaction worked or didn't work, as the case may be. And then I think just because we can see everything with the operanda or in situ measurement doesn't always mean that we can understand it. And particularly understand what is the causal parameter and or whether things are just correlated. But maybe the corollary of that is that maybe you don't need to understand everything and analyze everything, especially for your autonomous measurement. Maybe you just need to understand that it's changing. And maybe that's the first question. Is it changing? Do I have a reaction happening? And use that as the basis for some kind of decision. So I'm going to leave you with this kind of summary slide, but first acknowledge the people that contributed to this work, funding through the Genesis Center and the APS for giving us beam time to do this work. And I'm going to leave it on that summary slide where I think we need both fundamental understanding and our active autonomous control in order to achieve these new materials. So hopefully I left some time for questions.
Thank you, Karina. Thank you, of course, like a great overview about PDF again. It's So it's more a joke because Karina was working on the PDF station here at the APS, and of course she is always a cheerleader for PDF. Thank you very much. Other questions from the audience? Otherwise, I start with my questions. My most urgent question is, of course, like coming back to the beginning. You mentioned already like the ideas with spectroscopy to go for autonomous experiments. You have a lot of in situ experiments shown, like also done in a very clever way, how to be very efficient in doing many experiments and exploring a large space. So what is your idea also for scattering and diffraction? What could be an interesting approach to start seriously with autonomous experiments?
So many different things, and obviously, as somebody who loves PDF,
yes,
we did think about doing those measurements first. You know, I think whenever you're trying to do something, I mean, this is a little philosophical. When you're trying to do something different and new, there are always going to be so many different things to figure out. I mean, you know, if we were doing this scattering, could we analyze our data to the point that was going to allow us to make a decision? Maybe, maybe not. And so, you know, we chose the absorption spectroscopy because it would allow us to give us a useful handle on what things were, in order to make the decision, in order to get the loop going, and actually do it. If I was going to do this in diffraction, which would be a key next step, well, maybe it's not next step. Maybe it's like 5 steps down the road. There's lots of things that I could think of doing. And again, you know, we always think about what's our standard approach to doing analysis, which may be fitting data, refining a lattice parameter, whatever it is. And I think maybe that's a trap to think about, to assume that we would do autonomous measurements in the same way. If I was going to do autonomous measurements on these, my first question would be, you know, how much has the signal from the sample changed? And, you know, I started off my career doing a lot of thermal expansion studies, and or trying to figure out what temperature reaction happened at. And if I was trying to do that and I was just trying to step it through, maybe I'd say, okay, keep taking big steps until it changes a lot. Maybe that would just be a Pearson correlation analysis. Take big steps until the sample changes quite a bit, and then take smaller steps, and then take smaller steps. So you can think about different ways to control reaction, but not necessarily by doing a full Rietveld analysis. Maybe we don't need to do that in order to do something useful.
So in this case, it would be more doing the intelligent experiment steering, right? Because usually what we done in the past was like you set first like that's range of temperature I want to go, and I go as whatever step width. What you are saying is much more like, okay, we can also be more flexible. As soon as we start to see changes, we will start to change the step widths automatically to cut down and to go smaller steps. This is right.
Yeah, I think that's, I mean, that's how I would approach it.
Yeah. I think this is something like it's fairly, or at least for sure, like it would be the first approach. And I think it's something fairly simple to implement. What would be for you the next step after? Because I mean, something what I am fascinated about is, of course, like predicting with models, checking on models, see like there's a big discrepancy. So you can also model your expected diffraction data, right? Or your PDF data, compare it with each other and say like, okay, it's not what we wanted. So like, and how to try to move to this more similar way, right? So it could be also the exploratory state we're using modeling.
I mean, I think all these things we can imagine stepwise how to implement, and there's a lot of infrastructure that goes to implement it. Okay. I think the thing that I can't figure out, or that I think when it gets really hard, is when something unexpected happens. When it starts to go outside, it's outside the envelope. So yeah. Maybe that's the reaction happens differently because we didn't control for packing density, or we didn't control for something else that proves to be important, but we didn't know it. I think that's where things become difficult. But maybe that's the part where we always have to have the human in the loop, because
yes, it's getting close to my point of quality control. So are there more questions from the audience? If you raise your hand, I can see it. I'm trying to keep the whole screen under control.
Andre commented in the chat. Can I comment on how the sample environments need to be changed for autonomous experiments? And can we use the same sample environments? Let me see. I mean, I clearly use the same sample environments. I don't think there's any reason to throw out all the work that's been done to create good sample environments. I think there are some additional considerations. Like if you have to consider the dead time, right? So how, in the case where we're changing the gas flow, how long does it take that gas flow to be realized at the sample? Or how long does it take for a temperature change? There's some practical considerations. I don't see any reason why the same sample environments can't be used as long as you can control the variables appropriately.
Okay. Okay, if there are no other questions, I would like to introduce our next speaker. Dan Olds from Brookhaven. I think you can build up on what Karina said partially, right?
Well, I just overwhelmingly agree with everything Karina says, including that PDF is a great place to start with all this. And yeah, it's always great to see.
Yeah, you can go ahead. I mean, you can. So the last thing I wanted to talk to say about you is that you are coming from the experimental point of view, but you moved recently more and more into computational science, correct?
Yeah. Sort
and
of.
This makes it very interesting. Yes.
I keep going back and forth. My whole PhD was in theory, and then I went to beamlines, and now I'm back to I don't understand it. All right. So.
Okay. Thank you.
I'm Dan. I am. I hope the connection comes through. I'm actually representing. I should mention these are all my collaborators. I have both on a lot of the work. I'm showing off. Folks from both Brookhaven and NIST played a big role in this work that I'm going to be showing off. So I'm coming from the NSLS2. Specifically, my beamline is the PDF beamline, although today I'm in Oak Ridge, so it's a little strange. But the PDF beamline, if you haven't been there, it's very, very similar to the 11 IDB beamline, where I first met Karina at the APS. Major differences being better bagels, skinnier pizza, and a different giant metropolitan area. Yeah, so the other major difference is we run Blue Sky. Blue Sky being a Python-based backend that does beamline control and data acquisition. And everything that I'm going to show you today is really enabled by Blue Sky, because it lets us stitch together all these components. The infrastructure of it, the computing side that I have sort of been drawn into, it fits very well with this infrastructure in a way that we weren't able to get work easily with something else. So not to dwell on that, what's sort of my high-level vision here, AI at the synchrotron. I mean, the truth is, in many cases, our productivity at beamlines is no longer flux or detector limited. It's control and analysis limited. We're all feeling that. Automation and streamlining of data collection and processing will absolutely both increase our productivity and reduce workloads on staff. In situ, particularly adaptive in situ, I think Karina was making some great examples of how this can really advance discovery and science and all these things. But a lot of my focus has been more on helping users right in the middle of a measurement. Like, what are they doing right then? What is the insight we can give them while they're at the beamline, while they're driving things, so that we make sure they get the right outcomes they want the first time to make more efficient use of that beam time. So what are some examples? I just want to go through a few of the tools where we are using AI at NSLS2 today to really enable user science. One of the big ones is just, hey, I want to get a cup of coffee or go sleep. Dear AI, would you watch the beamline for me? We just did a very simple out-of-the-box supervised learning. We ended up training a Gaussian process on XFs. This is XFs data from BMM. Didn't take that many data sets. We just labeled good spectra and bad spectra, and we didn't bother getting into why it was good or why it was bad. You can do that, but we just sort of said, hey, something here is bad, like something about this. I don't know XFs, but I can tell the stuff on the right there clearly looks pretty bad to me. The beamline scientist labeled this and said, these are bad data sets. We built up a model, trained it, found it to be very, very accurate. And now, as data is being collected, even today, every single pattern that runs through BMM gets automatically analyzed by this little AI agent. And it sends a message on the Slack channels that are created for the individual beam times, letting the users and the beamline staff know, hey, everything looks good, everything looks good. This is just like a sanity check in case something, who knows what, goes weird in the middle of the night, or when you're at lunch or whatever. You don't want to end up in a situation that you come back and you find out all the data is junk and you can't use it. So this has been really nice. Another example, sort of say you're doing an in situ study. Karina touched on this very well. You want to know when things are changing. So say you're heating, this is an example where maybe we're heating a sample up. And this is a case where we happen to know that there are 4 phase transitions. This is my favorite example of barium titanate. And we're saying, hey, is my cryostream in a good enough position? Am I really hitting the right temperatures? I just want to know that the phases are in there, but maybe I don't have the SIF files handy. I don't want to sit and do a refinement and verify that I'm getting the structure. We can use simple tools like unsupervised learning, clustering and algorithms, agglomerate clustering, to just kind of pass this data to them wholesale without any pre-training, right? These are methods that don't require any, advanced training, and just say, hey, please sort this. What do you see? And it turns out that if you take this data set and hand it to agglomerate clustering, it says, I see these 4 groups. And by the way, those happen to match with the predicted phase transitions of barium titanate. I want to emphasize that this didn't know anything about barium titanate. This wasn't taught ahead of time what to look for. But the transitions are real. I mean, good news to us as crystallographers, the transitions are real. There is a legitimate difference there, enough so that these simple unsupervised methods can pick up on it. And just as a sanity check and as sort of like that first pass analysis of the beamline, tell the user in real time, your experiment is progressing, you're getting where you want to go. Constrained non-negative matrix factorization is something we developed. This is another method of a lot of these sort of decompositions where you assume you have components and weights, and you say, my signal is some combination of independent components weighted as versus some ordinate time, temperature, whatever. You can combine the components and weights to get your data set, and the point of these methods is to decouple them. PCA is a very common method to separate out weights and components, but it's not at all designed to or a guarantee to get you something physical out. It's really, I think of it more like zipping your data down into a nice compact representation. NMF is something I'm a big fan of. It happens to, by the nature of the fact that the components end up non-negative, it's very well suited for things like X-ray diffraction, where our signals are non-negative and they are additive. So in essence, it's a series of additional constraints that help kind of push us in the right direction. Constrained non-negative matrix factorization is one step further, saying, actually, I have some other constraint. I have a point I'd like to make, right? I know my starting phase, or I know my ending phase, or you can put something in there and say, you have to use this as one of your components. It removes some of that ambiguity. This we used, for example, during a molten salt experiment, where we monitored the evolution of this, the heating of this sample over time. We were able to identify mid-measurement, and it was a difficult measurement, right? It was a complicated thing working with molten salts. You know, they're not always fun. They eat through everything. We were able to identify a previously unpublished sort of intermediary phase that was existing here. And just by saying, hey, look, I noticed that there's a new feature that's emerged, but it doesn't look amorphous, right? It's still something crystalline, and it's going away as you keep heating up. So what did we do? We didn't stop where we expected to. We kept going. We kept the experiment going to a higher temperature till we reached the fully molten state, and we were able to, you know, complete the measurement, make the user happy, get the science done. And it's something that, you know, we would have eventually done, but this avoided a trip back to the beamline, right? This avoided going home, analyzing the data, and then saying, actually, we needed to get hotter than we did. Ensemble training is a way of addressing a situation where you want to train like a neural network to do classification, but you don't necessarily, you want to use synthetic data. So this is a problem we have, right? We can forward calculate a diffraction pattern or PDF very easily, but can we fully simulate all the effects that we see at say, a beamline data in order to capture it? Ensemble training says, I'm going to take some synthetic data. I'm going to train a whole bunch of AIs, not just one, independently or quasi-independently. Then when I hand them real data, I'm going to ask those individuals to vote. And by looking at how they vote, by looking at the set of the full ensemble, you get an idea not only of if one of them is clearly the case, but if there's ambiguity, you know, if they can't come to a consensus, it tells you that maybe you haven't trained up the system enough to reliably consider what it's suggesting. But it's a great way to take synthetic data and apply it to, train on synthetic data, apply it to real data. So we built one of these up called the X-ray crystallography companion agent, specifically for diffraction data. So once again, taking our friend barium titanate, we passed in 4 CIF files, gave about an hour to train on just a laptop. When we handed it that data, that barium titanate data, all little AIs ran around in there and voted. And in terms of like speed of calculation, right, the classification once these things are trained is 25 to 50 milliseconds. That's faster than it takes to plot the image to the computer screen. So if we're thinking about the sort of computational methods that are going to meet the speeds data are coming out, methods like this are very applicable to the future. And the results we got out were completely consistent with Rietveld refinements that we did on the data as well. So they were just as accurate. These are what you're seeing is sort of the vote tally of the different AIs as they decided the phases were. And then we did some stuff with reinforcement learning where we had, especially during COVID, we dealt with a lot of mail-in samples, and we had to address the case where, you know, say you have 200 samples and you used to have someone sit there and by hand go through and determine what's the best way to measure these. We basically weren't on site. We didn't have users on site to do that. So we trained a reinforcement learning method in order to automatically determine the best measurement scheduling, so to speak, of these individual ex situ samples, and found that this RL agent performed very, very well, particularly in cases where maybe your beam time got cut abruptly. Using this agent was shown to be about 100% improvement over the total data quality you'd get if you had just done a standard like sequential measurement. If you want to try this out, we do have these tutorials online. Unfortunately, the URL just got longer because our good friends at Binder lost a bunch of their funding. But we just had our user meeting last week at NSLS2. So if you wanted to go and try any of these, a lot of this is available, including trying out Blue Sky. on these Jupyter hubs we host online. All right, so that was a quick overview of some of the things we're doing in AI, and I want to impress on you, we're using these tools, but in a lot of sense, they've been sort of almost like piecemeal infrastructure. They're all built on blue sky, but they don't have an overarching connectivity, or at least they haven't until now. So I started thinking about this talk. What does the future of human AI interfaces look like? And like any, good student would do these days, the first things I asked ChatGPT. And ChatGPT came up with this rather prophetic statement. And I had DALL-E also come up with an image saying the future of AI and human interfaces at beamlines. And it created this image, right, which I kind of like. Overall, the future of human AI interfaces beamlines is likely to be characterized by a combination of automation and interactivity, with researchers using AI models to quickly analyze large amounts of data while also retaining the ability to directly interact with and interpret the results. You heard this. Karina was getting at this, and I cannot agree more. We're not going to be removing human researchers from the equation at all. It's going to be working in tandem with AI. So what kind of infrastructure, what does this start to look like? Well, for one thing, right, what are the different agents you're having? They're not all neural networks. There's these data clustering methods, there's decomposition methods, there's classifier methods, there's room. So this isn't just 3 agents, right? There's multiple methods for each of these that you could imagine running during a beam time. And then there's multiple instances of each of these agents. If we were to pick NMF, one of the things you have to decide is maybe like how many components you want. Do I want 3 components or 20? Ultimately, that means I probably want to spin up 17 agents and have them all going at once and feeding me back the results. And furthermore, right, some of these results, they feed into each other. I can have agents talking to agents. I could be taking raw data, using PCA on it to reduce its dimensionality, and then feeding that into some sort of clustering algorithm, right? So as we started to think and work like this, we realized we needed a workflow. We needed a way of gluing all these things together that was extensible and interfaceable, and not just sort of a one-off. So this is kind of what we came up with. I call it the adjudicator model, or the adjudicator Q server model. The idea is you have these agents, right? And they're out there and they can read the data coming from the beamline. And there are all kinds of agents. And they're performing some analysis, calculation. They're putting that forward in a place that the user can read it, right? They have a visualization front end where you can configure them. But also maybe they're making requests. They're saying, this is the measurement I would like you to do. And you actually don't want all your agents screaming onto the beamlines. You need to put something in the middle that we started calling the adjudicator to sort of be the judge. That's the thing that ultimately you as the user need to talk to and can pull the plug on if something goes wrong or can adjust. It's kind of like if you're sitting at the beamline and 6 people are giving you suggestions as to what to measure next. It's up to the person sitting in the chair to decide who you actually listen to. That's what you adjust, the knob on the adjudicator. Those are being put into the queue server, right? So individual scans are being placed in a queue, but you can also still adjust that queue. You still have ultimate authority as the human researcher to say, no, I want to put plant. No, I don't agree with what the AI says. I really want them to look in this direction. Those commands from the queue are executed in the beamline. That data is then shared once again, and the agents can once again digest all that new information and start changing their predictions. So we did that, and we performed what is like the coolest thing I've ever done and continue to do, these real-time multimodal measurements, completely run by AIs. Multimodal, of course, I'm sure in light source community, I don't have to talk about the importance of this, but measurements that take advantage of many of the capabilities that we have at these big facilities, such as the cell that's designed to allow for XAPS total scattering microprobe imaging. We specifically were thinking about combinatorial materials, things like high entropy oxides, high entropy alloys, because this is a family of materials where a single measurement is just not going to give you everything you need about them. You really need to combine multiple techniques. Oftentimes that unfortunately requires multiple visits to the beamline and taking your sample around the ring. And this is exactly what I noticed, speaking to one of my XAFS colleagues, Bruce Revel, we said, you know, a lot of our users, they measure stuff at my beamline, your beamline, they go back and forth. There are methods to sort of combine that, like after the fact, to analyze things using stuff like RMC profile. But the multimodal aspect of these measurements really isn't coming into play until long after the measurement is complete. What would be great is if these two beamlines that were somehow separated were together, but they're not, right? They're well separated by a tricycle ride. So we thought, oh, maybe we have the users then, we schedule their beam times together, right? That they're talking on the phone with each other from one beamline to another, helping guide the experiments. But of course, why do that when you could have an AI do it? So we wanted to autonomously and simultaneously drive both beamlines, PDF and BMM, leveraging all the information in real time from these measurements to make decisions in both directions. But there's a lot of stuff you need to address here, things like the multi-fidelity aspect. One of these measurements is very, very fast. One of these is very, very slow. And they're both controlled, although using Blue Sky, with different interfaces. We needed to be able to monitor it. We needed to be able to step in if the AI started doing something particularly dumb or bad and redirect them or just take control. We needed to perform this work safely and securely, right? We were now talking about moving data around a network and moving commands to beamlines around a network. That's very different from, I think, a lot of the paradigms that we are conventionally used to controlling beamlines in. And most importantly of all, we didn't want this to be a one-off hero experiment. We wanted to do this in such a way that if we want to extend this to other beamlines, if we want to extend this even across other facilities, there's a path to do it. Right? So the sample we looked at most recently is a platinum zirconium film. We've done examples either where we break the sample in half, so we're sure we're looking at sort of the same. So it's deposited film on both directions with these two metals. This is not a particularly scientifically interesting material, but it was a good commissioning sample. So either make two duplicate samples or break it in half. The diffraction measurements are fast. The XAFs are slow. In addition to the fast diffraction, it could kick off PDF, which was a little bit slower because it had to move the detector and measure a bit longer. But the phases were being determined in real time by machine learning, and it was being applied both to the XAFs and the PDF. So Blue Sky Q Server was controlling everything. Here's just an example of sort of these scans going through, and you're seeing as the AI is jumping around, sort of making its mind up as new information comes in about what it thinks are the most critical regions of the sample. Again, this is the coolest thing ever, right? Like I'm standing here watching an AI, watching like 20 AIs actually, argue with each other and drive two beamlines at once. This was a highlight for me. So real quick, some of the stuff we saw, for instance, this is the data that shows high platinum content on the high X on this plot, so with positive X on the wafer, high Y plot. I apologize for the names. High zirconium content on the bottom. We see that the sample is very disordered. We were hoping for something more crystalline, but you know, it's a commissioning study. What do you want? But clearly, there's different features to look at here, and our ordinate we could explore was just moving the wafer back and forth. Looking along this wafer in X direction allowed us to effectively change the composition that we were probing. The model-free attempt experiment strategy we decided to use, and I'm not saying this is the best one, but this is just something we came up with that worked for us, was to initially perform classification or clustering on the data set. We used k-means. It worked. It's simple, but if it works, it's not dumb. It's great. We construct a model from the results. So we asserted that the centers of the k-means must have been the individual phases. We re-examined the data set from the vantage point of the model, which really just means classifying all the data sets we've measured so far in terms of their distances from the centers. And then we selected the next points to measure based on the perceived uncertainty in this model. You heard this come up a little bit previously. Any sort of these autonomous measurements really do need some kind of model behind them. I don't think it needs to be a particularly complex model. It just needs to capture the details of what you're exploring, which for us was uniqueness of phase information. We did have, or here's an example of that in place, where, for instance, say you had these 6 data sets measured, this particular algorithm would say, oh, measure here next. So you'd rerun it and it'd go, oh, now measure down there. And so you can see it just sort of builds up based on what it's seeing, where it thinks you should measure next. It's prioritizing unexplored regions, following by things that it just wants to know more about. That's what's driving the XRD. That was our agent that was sort of driving the fast XRD exploration. So it didn't have to be clever because it was fast. For the slower measurements, driving the PDF and the XFs, we did have a slightly more clever function. I can't share the details of it with you yet, but we call it the scientific value function. It effectively prioritizes inquiry into regions of dramatic change in the measurement data and deprioritizes inquiry into regions of linear or no change, with the thought being things that aren't changing aren't interesting and things that are linearly changing are too easy to model. So let's go to the regions that don't fit that. So here's an example of sort of the full data collection that we ended up with at the end of the day. We can clearly see different phases across the wafer. Some of these overlap, suggesting it's not at equilibrium. But again, you work with the sample you got. This is just another view of the data. You can see those different regions. And maybe by eye, you can look at that and say, yeah, this, like I would put the phase transitions roughly in this position. And for example, if you were to pass this to k-means, this is where it would approximate those changes and transitions. And the fact that it clustered these in terms of like all the blue is together and then all the orange, it didn't need to do that. It doesn't know anything about the coordinates spatially. It only knew about the similarity of the patterns. So this is a really good indication that there's something physically correct about this clustering. I again need to give credit to the enabling technologies and DSSI, our data science and systems and integration team. A lot of this back-end stuff we had was already in place to make this happen. It's things they've deployed over the last couple of years. It really took this from being sort of a hero experiment to a hobby experiment. But I give them all credit for putting this infrastructure in place. So I'll conclude by saying, you know, AI and automation are going to play a huge part in the future of our beamlines. It's too limited of a resource and too valuable of a thing, not for this sort of obvious marriage of technologies not to happen. The degree of the integration will vary from beamline to beamline, but it's certainly coming. What's important, I think, is that we make sure these methods are accessible and easily interfaced with our staff and our users. I think we don't want to be reinventing this infrastructure every time. We want something that, you know, if you want to use this, you can just, you know, pip install it and have it on your beamline. And if you come up with an idea for a new agent, you don't need to reconstruct the infrastructure, right? You just encode your agent in a little bits of Python or whatever, and it should just plug and play. Everything I showed here was really possible with surprisingly little effort because of Blue Sky. We feel this adjudicator Q-server method works really well for automation. And it also readily interfaces with distributed computing, which I think is another big part of this, right? All these things that I was showing, all these agents, they weren't running on a computer in front of us. They were running somewhere else on a server farm. But this model really allows yourself to use resources from a non-local environment. And really, we're pushing towards self-driving beamlines with all this. So thank you. My boys, they got to come for Take Your Kids to Work Day. And I'm really trying to build the beamline capabilities so I can spend more time with them and show them cool Star Trek-y level beamline science when they got there. I'm happy to take questions, comments, or collaborate with any on this.
Thank you, Dan. Always interesting to hear. Just a comment from my side about like we have always enough flux. I would gently disagree with you here. I love flux, and as long as it takes me a minute to take a PDF pattern, it's too long for my taste, right?
That's fair. I would say flux is often not our limiting factor, though. I usually have a minute.
Yes, I agree. I agree. It's often not a limiting factor. For some stuff it is. So it's more a gentle disagreement here. John, please go ahead.
Yeah, that was just an absolutely terrific talk. Thank you very much. I really enjoyed that. So I want to just kind of probe a little bit more into this adjudicator tool or model you have. I think it's really neat. So first of all, maybe you could just say a little bit more about it, but how complex of a kind of decision making can you build into this thing? Can you have sort of Boolean kind of constructions, like if you see feature A, do this, if you see feature B, do that, this kind of stuff? Yeah, it's
exactly what you imagine. It's just the real reason for the adjudicator was we did have a time where we had runaway agents, right? You know, like the sci-fi movies where you're like, how do I kill the computer? We had that, right? And luckily we Control C is very powerful, and closing SSH connection is very powerful, but just realizing that this is not a way to go forward, and we needed some middle authority that had special permissions, especially if you start thinking of a future where users aren't only bringing samples, they're bringing their own agents, right? They're bringing, especially with groups like the Chapman group out there, right? They're going to be there with the agents saying, this is how we're going to drive our experiment. We need the USB plug for them to connect it in. And we just wanted to have the confidence that a user couldn't accidentally do something that damaged the beamline or their own experiment or anything like that. But it's not complex, right? It uses an ask-tell system. I'd point you to the GitHub repo of it. But it basically just says, like, things can shout at it. I think we use Kafka currently to communicate on the message bus. It just listens for things, but then you, as the human in the middle, can configure it and say, which one do you actually listen to, or do you ignore everybody? So putting in more clever logic as to like when to switch between them, that's something we've discussed. We haven't put it in place yet, other than on a timer. We used a timer of like, for 5 minutes do this, then switch to that. But we've largely just used it through a knob. So.
Thank you. Wencheng, you have a question?
Yes, it's the question about, hey, Dan, it's Wencheng here. So
how's it going?
Good, how are you?
I'm good.
I'll see you in the summer.
I know.
One thing I didn't get, maybe I didn't pay much attention, is the second example, the wafer experiment.
Yeah.
My understanding is that you're trying to explore the disorder state or the variation of phases at different points of the wafer. But my question is, for the running at both beamlines at the same time, and especially you're on 2 different samples, right? You break them apart, you put different sample, but the result from one beamline, what's the guidance of the result to the other beamline? Are you going to motorize the other one?
Thank you for bringing this up, because I think I went through this quickly. In this example, we needed 2 identical samples, because we wanted to say, if you go to, we needed to have a reference frame that was the same. So if the PDF saw something interesting at x = 5, it could tell XFs go measure x = 5. And
it
vice
has
versa.
to be the same. Okay.
So it had to be the same. So to do that, we had 2. We did a couple things. We had multiple wafers made, and the people making the samples insisted they were the same. We checked, they were same-ish. So there is a degree of, like, we were worried about that tolerance, and that's something that we're currently sort of coding into some of our agents of how to handle that difference. But when we wanted an absolute difference, what we did is we broke the wafer in half. And then we only traveled right on that edge, because we said, right, if you cleave it right in half, right on either side of that is going to be identical. So in that case, they were truly identical samples, and we've run under both conditions, and it's pretty robust. So
yeah, that makes sense. Yeah, thank you.
Thank you. Gilad, you have a question.
Yeah, could you speak to the difference between your constrained NMF and a Bayesian NMF? So, where priors are defined? Is yours probabilistically solved, or are you just
No.
solving a objective function?
It's solving an objective function. So they're functionally very similar, but the way that they're numerically solved is different.
Okay.
To put it that way, but that is Bayesian NMF is another good way to go.
Okay, thank you.
Thank you for asking
Okay.
questions. I love my CMF stuff, so I always want to talk about them.
Okay, if we have no further questions here to then, I have one more, sorry. This was puzzling me. So I liked it, of course, like to run two beamlines in parallel. It's cool.
That's awesome.
It's awesome. I can see the point, but often it's hard to do, but not because
Hard to
of,
schedule.
yeah, the hard to schedule. It's of course another point, but it's also hard to do because sometimes you pick different geometries, different sample thicknesses for various methods, right?
Yes.
So what would you say, what is the percentage of application you could see, you can envision? 10% of the experiment possible where you really would like to have two methods?
I think it depends on what the field is. So in terms of true two beamline methods, the high entropy alloys, high entropy oxides are particularly spicy right now. We're getting a lot of users in that area, and many of them want to produce wafers full of samples. So if I got this up and running, I have like at least 30% of the beam time that could be consumed by it right now. That was not the case 10 years ago. I don't know if it will be the case 10 years from now. I think you would need to have measurement cases that are particularly well suited to it.
Yeah. Okay.
Now that said, being the PDF beamline, right, we have the capability to do PDF, we have the capability to do diffraction, we have the capability to do SACs. We can switch between them. So I can kind of multimodal my own beamline. So from future-proofing, I'm personally not.
Yes.
But,
yes.
Yeah.
I mean, that's something I see for sure. I mean, all these non-X-ray secondary methods are out there, right? And you can apply a lot also for cheap money. It doesn't have to be very complicated. Karina gave the example of the drift. This is more the high-end way and also expensive from the setup time and so on. But there are also others like Raman spectroscopy, where you at least can go so far, of course, not to the high-end quality of the secondary method, but at least to the level that you can combine experiments you have done with real instruments, like real Raman systems, and to combine the data at the end. Because these handshakes, these are the important parts, right? And how to realize them. Yeah, thank you. So thank you very much. It was good to hear from you and get an update. Our next speaker is, I hope I pronounced your name correctly, Gilad Kuzny from NIST. Actually, you were mentioned several times yesterday already because you have a great impact on materials discovery, and many people are collaborating with you and showing examples with your high-level input. And now I'm really curious to go to the source of information and hear what you have to say about autonomous materials discovery.
Thank you, great. And also, Daniel, I'd be very interested in, I'm going to talk very high level, and I'm also, one of the things I'm going to talk about also is multi-agent. And so I'm curious to hear, Daniel, your point of view, because I'm not sharing my screen, since we're both working towards a similar goal. Share screen. Okay. So I should shoot for like half an hour. Is that the goal?
Roughly, we can go into the break. So also yesterday we cut down the break to 15 minutes, which is still okay. Okay. So can you see my screen? Yes. Okay. So the first thing I want to say is, as you've seen other people talk about autonomous systems and machine learning for autonomous systems, we've run a bootcamp for, I think this will be our 8th or 9th year.
where we teach everything from intro to Python all the way to how to build a fully autonomous, system. So if you're interested, please either contact me or go to this website. It's all hands-on with Python and real examples. Okay, I'm going to skip a bunch of things. Okay, so I'm going to hop around a few topics, but at NIST, we have a bunch of different focuses associated with autonomous systems, building robust platforms and building enabling technologies like Blue Sky, educating customers like the bootcamp that I just mentioned. But my primary focus is building physics-informed machine learning. So looking at how can we best encode prior knowledge into machine learning and then demonstrate that, see if it's actually better than off-the-shelf machine learning. So we're interested in a few general techniques. One is autonomous metrology, as you've seen many times, where the machine learning controls a measurement instrument, and also fully autonomous systems, where machine learning actually makes the material, measures it, etc. And the benefits of autonomous systems have been mentioned a bunch of times, so I'll just skip that. We came to this challenge, we came to machine learning driven material science and physics through the challenge of being able to more rapidly identify the structural phase maps of novel material systems. Since the structural phase maps are a material's phase is highly predictive of its functional properties, it's important to have these maps. These structural phase maps can be used to guide us towards finding novel materials. For instance, in some cases, new optimal materials will occur within just specific phase regions or along phase boundaries. So if we can quantify the structural phase diagram or phase map of a novel material system, we can use that to help us find new materials. Our first go at this was trying to do autonomous phase mapping, where we had these combinatorial libraries where each point on this wafer is made up of a different composition. And we were curious to see, can we figure out if we took this wafer and we loaded it into a high throughput synchrotron X-ray diffraction system, could we have machine learning guide subsequent X-ray diffraction measurements to maximally give information about about the phase diagram? So this is from back in 2015. So in this case, we have our wafer over here. The correct phase diagram information is over here, where we have our phase boundaries. Each of these circles is one of the samples on the wafer. It initially makes a prediction as where it thinks the phase boundaries are, given some prior knowledge. We import knowledge from external databases as well. Let's see. And then, so it picks a point that it thinks is highly informative for maximizing knowledge of the phase diagram, which is indicated in red. It measures that sample for XRD, it updates its prediction, picks a new point to measure. And in this case, it was using a risk minimization. So it was trying to minimize the likelihood of misclassifying a material based on its phase region or its constituent phases. So this was something that we started off with. But we realized that because of the relationship between the material structure and its functional properties, if we can maximally learn about the phase diagram, maybe we could exploit that and try to find new materials. So we came up with this Cameo closed loop autonomous materials exploration and optimization, which combines two different tasks. One is phase mapping, and the other one is trying to do materials optimization. And the thought is, by combining these two, maybe we could accelerate materials discovery. And this combines some of the techniques that we've already talked about, active learning and Bayesian optimization. I won't go into them, but here's an example where, in this case, we're trying to find the best. In this case, we're looking at iron, gallium, palladium. We're trying to find the material with the maximum remnant magnetization, or I think saturation magnetization, which is indicated color-coded here on this diagram. The best material is the one in yellow, the ones over here. And we have the phase diagram shown here, where the phase boundaries are. And what this original algorithm, Cameo, did was it would first select samples to measure for XRD, and it would learn about the phase diagram. So it's first learning the phase diagram. Then once it learns the phase diagram, it then says, okay, since phase is tied to functional properties, let's now choose a segment of our search space and just narrow in on that space. So we're not searching over the entire search space. We're just looking at the most likely areas of highly useful materials. And it then, so converges to function. And then it just starts hacking away at this region. So what we found is we get a order of magnitude improvement in over off-the-shelf machine learning methods and active learning methods if we encode this knowledge that the phase diagram is important. So it more rapidly hones in on the best material. And yeah, again, this is because often the best materials occur near a phase boundary or within certain phase regions. So you're basically hacking apart the search space and just looking at certain regions that are useful. And we can also incorporate a lot of external knowledge, for instance, density functional theory or other functional property data. And we were able to use this in control of the high throughput X-ray diffraction system at SLAC to accelerate the discovery of the, I believe this is correct, the only novel solid state best in class material discovered by an autonomous system, which is a phase change memory material, which we published in this paper in 2020. So it's being used by the Semiconductor Research Corporation to build novel devices. So this is, as far as I know, the first and potentially the only best-in-class material discovered by an autonomous system. And we also looked at if we encoded different levels of physics into the machine learning, do we get a boost? Like how much physics, where is the best place to encode physics to get the best boost? And this is this paper, Physics in the Machine. And it turns out that we found that the best place to encode physics was in the decision-making. It's more useful to encode physics in the decision-making than even in the prediction-making. But when you encode physics at every level, you get significant performance boost in phase mapping and materials optimization. Okay, so that was the past. More recently, we decided to try to expand the application of these types of things. So Austin looked at applying our physics-informed approach towards optimizing neutron diffraction experiments. So in this case, we encoded both so we were studying a magnetic sample, and we wanted to more rapidly hone in on its structure parameters, specifically the Neal temperature and a bunch of other parameters. So what we did was, since we're using neutron scattering and we're studying magnetic material, we encoded magnetic physics and we encoded neutron scattering physics into the machine learning. And so then we got a dramatic acceleration, 5x acceleration in honing in on these properties. So in this case, the system was able to select which 2 theta angle is the most optimal to measure next, and also what temperature is the most interesting to measure, to investigate next for honing in on the Neal temperature. So in this case, the autonomous system was controlling 2 things: the angle of the detector and also the temperature of the sample. More recently, we have we started thinking about the combination of theory and experiments that often you have experimentalists working on one track and theoreticians working on another track, and they come together every once in a while. So can we build a machine learning tool where the active learning segment, the decision-making segment, decides, can control both this computational experiments as well as real-world experiments. And by including this, by having the machine learning be able to run theory experiments, run computational experiments, the hope was maybe we could have better extrapolative capabilities. With all of the machine learning techniques that you get off the shelf, in general, you get very poor extrapolative capabilities. You're very good at interpolating between samples that you've already made. But if we can encode more physics by having control over theory, maybe we could have a really good extrapolating machine learning code. And so for this experiment, we synthesized a combinatorial library which has a composition between over a certain range of this binary, and our system was able to study phase diagram again here by doing X-ray diffraction measurements, and it's able to run CalFAD calculations, thermodynamic calculations of the material. And the thought was, based on just that information, will we be able to predict where the, I always forget the name of this point. I can't remember the name of this point, but this characteristic. Eutectic point. Thank you. So eutectic points, yes. So we have information over here, but by including also theory, can we do long range prediction and figure out where the eutectic point is? Thank you. So this is, let's see, can I get rid of this pointer? So here we have, so these are the samples that the system is measuring, is figuring out where the phase boundary is, which is indicated by red, and it's controlling the temperature and the composition that's measuring at. And you see here that at every iteration is also making predictions based on the CalFAD, the integrated CalFAD calculation. So the experimental data is used to inform the CalFAD calculations. The CalFAD calculations are used to inform the experiments, the analysis of the experiments. And so that both pieces of information are tied together. And you can see that, the system is able to make some prediction, and with more data, it's starting to make probabilistic distributions over the phase diagram. And with this information, we were able to, for this thin film non-equilibrium material, be able to predict where the eutectic point was, and we synthesized that sample and verified that the calculation was correct. Okay, so that I rolled through, so that's 3 subjects already. So now I want to talk about what Daniel was also talking about, which is multi-agent stuff. So this we published in this paper in Matter, this scalable multi-agent lab framework. And my thought is maybe, some of the stuff that we've developed, because I know Blue Sky is incredible, maybe we can work on integrating some of these physics-informed methodologies into, work together and potentially work on integrating into Blue Sky. I showed Cameo, this method that's able to, run, all these methods are able to control experiments in the lab, analyze the data, and then make decisions. So the thought was, can we scale this up by having multiple agents analyze the data together, work together to analyze data, and also have them work together in making decisions. And we looked at a few different options. One where we have a central agent that's analyzing all the data and making decisions. In this case, if you have a big lab, all the data is coming to one central repository. And so then you have issues of bandwidth, in case you have detectors that are high volume output. Then there's the option of distributed. Can we have agents that sit on the instruments. So each agent is sitting on an instrument, and it is knowledgeable of that instrument. So it's physics informed of that instrument. So an X-ray diffraction agent knows X-ray diffraction, right? The physics of X-ray diffraction. And an agent on a scanning electron microscope knows scanning electron microscopy, right? And they're able to work together to learn. And then finally, a multi-agent one where they're also able to make decisions jointly. So not only unique individual agents, they're specialized for their own applications, but they're also able to work together to solve a problem. Yeah, so the argument that I have is, if you have a big facility, you will have big data and limited bandwidth. So having local learners is a benefit. So learners sitting on each instrument. So instead of sending the full data that's collected on a big detector, you would instead have that agent learn from that, from that data and condense it into something much more consumable. So instead of like a big SEM image, or you would have just the name of the phase that was identified, right? So much more easy to transmit. You could have agents with targeted expertise for specific problems. You could potentially have those agents optimize both local and global resources and decision-making. And the agents could be dynamically, their groups could, they could form teams based on the current challenge. And we have other interesting challenges like trust but verify. So maybe two agents are working together. They could, if they were using a probabilistic framework, they could have some belief system. Okay, I believe you, but I want some level of verification. So then that agent might do some kind of check. Yeah, you can have scalability because agents, as Daniel pointed out, you could just copy paste them, lots of other benefits. They could protect IP of the instrument or of the measurement, that because you're interacting with the agent instead of the original data. So again, we were looking at independent agents solving problems, agents being able to share knowledge, and agents able to share knowledge and make decisions together. We defined a framework for controlling labs using this we called multitask. And we looked at this challenge of trying to, again, do materials optimization. Can these agents identify the best material? In this case, we're looking over this composition space, and the best material in this case is, I forgot what we were looking at specifically, but I think maybe this is again phase change memory material. But so we're looking for a material that has both maximum of this functional property, and we're also interested in figuring out the phase diagram. And so what we did was, I don't have a graphic for this, but we have agents that are specifically knowledgeable about the functional property, and we have agents that are specifically knowledgeable about structure, about phase diagrams. And so the phase diagram agents are interested in maximizing knowledge about the phase diagram. Functional property agents are interested in finding the best material. And by collaborating together, we found that, so in this case, I didn't copy over the legend, but basically the green curve is the agents working together. The blue curve is, blue curve is the agents working together by knowledge sharing. Green curve is where they're knowledge sharing and making decisions jointly. So we show that you get a dramatic acceleration in materials discovery if the agents are working together. Okay, I think I have, maybe this is the last topic I have. We're also interested in educating, spreading these capabilities to the rest of the community. And one thing that we've done is we've developed this thing called Legolas, low-cost education platform, Legolas low-cost Yeah, education. I can't remember what it stands for. Somewhere in here it probably says. But the basic idea is it's an autonomous kit. It's a kit made out of Legos and some other parts, a Raspberry Pi and other things. It's a few $100s. We've used it for two years already in courses at University of Maryland. So the students build a robot and then use this robot to then do autonomous science. In this case, primarily they're focused on autonomous chemistry, where one of the challenges we provide them is, can you learn the Henderson-Hasselbalch equation, or at least the relationship between the ratio of mixtures of acid and base and the output pH? And they're using just off-the-shelf, safe materials in this robot. So it's basically vinegar and baking soda. So it's just mixing vinegar and baking soda, right? So we have them solve a bunch of challenges. One was, we're not going to give you the physics. Use a Gaussian process. Try to use a non-parametric method to learn the relationship between the mixture of acid and base and pH, and they were able to do that. Then we gave them the equation for Henderson-Hasselbalch, and we told them use Bayesian inference to figure out what the parameters are, or at least use active learning. Oh, sorry, I should mention this. In this case, for the GP, they used active learning to pick the next most informative point to get maximal knowledge of the trend. In this case, they were using active learning to figure out what's the most useful experiment to do next to get maximal knowledge of the parameters. Yeah, and here's an example where they, within 3 data points, they're able to figure out what the correct values of the parameters are. And then we had another challenge where we said, okay, we're going to give you 10 possible explanatory relationships that could explain the relationship between acid and base and pH. Use active learning to narrow in on the correct model. And in this case, they used entropy to, sorry, I have a bunch of slides on this. So they used entropy to narrow in on the most informative model. And then the final of these, let me see, yeah, I realize I'm talking extremely fast, but yeah, so the final of these models is, or the final challenge we gave them was, assume you know nothing. The robot, we want the robot to find the correct function. And we explained to them about symbolic regression and gave them a tool for symbolic regression. And so then what this thing does is it collects a data point, finds a set of equations that could explain that data point, and measures them based on how well they fit the data and how complex the model is. Then use entropy to narrow in to figure out what's the most informative experiment to do next that best differentiates between these models. Do that experiment and then repeat. So now we have 2 data points. So figure out the best candidate models that explain those 2 data points. And then now we have a set of models, use entropy to figure out to best differentiate between these models, and then collect the next data point. And within about 5 data points, they were able to using symbolic regression, they were able to find the correct model. And yeah, so if you're interested about this was published last year. We had all of these exercises. This was the 2nd year that we ran it, so we wrote a paper about it. And we're currently working on making Legolas a easily distributable kit. We have a few universities who are sending faculty over through an NSF-funded program to come and study with us on how best to incorporate these toy systems into their classes. And the last thing I'll present in this whirlwind of information is we have this website which we're working on improving called REMI, the Resource for Materials Informatics. And the goal is, everybody here probably has some notebooks that they've built for applying machine learning or data science to materials data or physics data. We wanted a searchable database where you could search based on data science tags, like what machine learning algorithm was used or what data source was used, material science tags like was it SEM that was used, what kind of material was studied, all those types of things. So basically a searchable database. And I think, yeah, that's it. I guess we have a bunch of fully autonomous systems, but I don't have any good slides on those yet. So I'll just end. Say again?
No worries.
Yeah, and I'll just end with this slide again if anybody's interested for our boot camp. Yeah, so thank you.
Thank you very much. And I really enjoyed also this showing like what you're doing to train the next generation school kids. I think it's a great idea to go with Lego and Raspberry Pi. So Lego, everybody loves Lego. And
yes,
and Raspberry Pis are very cheap and at the same time pretty powerful for what they can do and very easy to expand, right? So very nice explanation. Other question to Gilad? I'm just looking here on these ones.
I've got a question.
Then go ahead.
So this is awesome stuff. I want to just repeat what Uda said. I love this Lego list. Also that you named it Lego list. That's pretty great. So coming from, I'd be very excited about looking to incorporate, the interface between this and Blue Sky. As I'm sitting down the hall from some of the people that you interfaced with the neutrons.
Right. Yeah.
So I guess just a general perspective from your experience here, making these sort of physics-informed agents, what do you think, and I know this is a big question, what is the most important considerations when thinking about this sort of metadata schemas from an upper level? Imagine I'm thinking about a lot of beamlines, a lot of measurements here. What do you think, coming from the side of this, of all these physics-informed models, what are you wishing was there that is often not?
Right. Yeah, so everything, obviously, every piece of information possible, right? Because, you could have two people run the same experiment on the same piece of equipment, and based on the humidity, right, the results are different. So I realize it's impossible to collect, right? We basically need a full simulation of reality to be able to properly, right? In our case, your case is clear. You guys are making robust tools that everybody can use. Our focus is more on demonstrating these physics-informed machine learning methodologies. We're now building them into a tool set called Hermes. And so, right, so we're more interested in just the physics-informed machine learning. So hopefully my hope is that, maybe some of those functions could just be called by somebody using, or it could just be, Hermes could be obfuscated and it would just be part of Blue Sky. A Blue Sky user would say, okay, I'm working with XRD. I would like this type of agent. But exactly what you're saying, the metadata is incredibly important. And in some cases, we're looking at methods that could potentially relax the need for some of the metadata. Extracting knowledge from data where metadata is lacking is a common challenge, right? So, there's so many challenges in this space.
That's the relaxing. That's an interesting. Yeah. Sorry.
Wait a second. I have to interrupt here. So when you're saying lack of metadata, I understand it in this way that you have your agent, I would call it workflow, I guess, that your agent would know this metadata and has already applied the metadata. And that's the reason why you can live without the information of the metadata, right?
That's an excellent point. Yeah, because the hope is that the agent has condensed the knowledge. So
Yes.
If you've taken an let's say you're taking an XRD image, detector image, it now knows all of the detector physics. So it knows how to properly map the original image into a QChi image, and then unwrap and then take the QChi and turn it into a powder diffraction image. And so then when you send off the powder diffraction image, it would be in Q space instead of 2 theta, so people don't need
that's
to know.
The point. That's the point. That's the point. Because so, I just wanted to make this point when you called it like diffraction data, because I still many colleagues who love to share 2 theta plots. My first question is, of course, like, what was the wavelengths? And that's something like and then I've seen people transferring data from us into 2 theta data with the wavelengths of kappa chi alpha, because it's a lab instrument, right? So I think at least here there should be a kind of agreement, like what data are, and I would always hope that people decide on Q.
And Q. I was just gonna say Q.
And if there's a shoulder to your peaks, you know, knowing if that shoulder is actually materials dependent or is it from the source? Right. Like, you know, that information is lost. So yeah.
But I can see the point in it, to say like, okay, we have workflows, we have agents who do all the stuff because it's too much to deal with. Because if you have different agents, what my understanding is, in principle, for me, these are workflows, and these are workflows that run in parallel, because it is a high parallelization of the data. And then only for the decision making, you merge it into one workflow, combining all other workflows, right?
So it's not important. It's not required. So in this case, well, yeah. So in this example, in the multitask example, we can have agents that are individual agents who decide to work together, and so then they could share some information. Or you could have sort of this more communist point of view where all the agents are sharing information and then making joint decisions.
I see it.
Yeah. So.
I get the point. It's very interesting. Saul, you have also a question?
More of a comment, which is based off something you said, which is something to be careful here is, you know, you said, oh, it knows all the detector physics and pulls it off, so it doesn't have to have all this as much metadata. There's a lot there. That's a very dangerous statement that I would strongly discourage, because what might be knowledge about, is there a peak there in one, is that real or not in one setup, in a different setup, at a different detector, a different beamline would give a completely different set of answers, even though they seem similar. I think there's a little careful there.
But you'd have knowledge of that beamline, the detector, the source, all of that knowledge would be encoded in extracting knowledge.
So I guess you're saying the agent would then be very specific to that beamline with that detector.
Exactly. So that's exactly the case. These agents are, the whole point is these agents are highly tuned for their application and for their tool. And
so then the agent is the metadata, is really what we're saying.
Yes.
Okay.
It's protecting you from making inappropriate decisions about because often users will come to to use something and they don't have a good sense of the important metadata, and so potentially the agent would collect that metadata, analyze the data for you, but then because it's been tuned by the local experts, it's recorded the correct metadata that you might need in the future. When you're because whenever I get data from a beamline, it's often not provided with enough metadata. So
such as the distance to the the center of rotation or something. I guess
Right.
we've had a lot of postdocs that never measure that in any way, or even kind of do an experimental measure of it. And again, if things are you're doing something always the same all the time, I'm not sure Udo's beamline, I think she's much more flexible than that, and others. So it comes back to that, yeah, the stuff that goes with that detector isn't just something you can snap and know what it is. I mean, unless there's somebody who's taking responsibility each run, each experiment, each configuration to document all that. And that's actually not done now, right? So how is it going to be done better later?
Yeah, I agree with this point. And I would like to add here something. So with the metadata, I think it's also coming to the point, like coming back to my preferred point here, how do we deal with data quality, right? So what is the measure for it? Because if you somehow fold it in, then I can go with it, right? But otherwise I would be super careful, because it really, a lot of information gets lost. So as Carol pointed out, like where's really the point, where's the confusion, what do you really actually have, right? And that's something like it should be in the metadata for my taste, but it could be somewhere else. But then it has to be really go in a severe way of how to judge the systematic errors and the statistical errors on top of it, so that you really know what your errors are, because that's what it is at the end, right?
Yeah. And so all the methods that we're focused on are most of the methods we're focused on are fully probabilistic methods, and the goal is to encode as much of that metadata so that we have a propagation of uncertainty from data collection all the way to model prediction and decision making.
Yes. Thank you. Are there more questions to Gilad? Otherwise, so I could ask more. But for the sake of time, I would like to stop here for the break. Also, yesterday we did it that we said, okay, we expanded to 3:20, that we have a 15-minute break for people to get a coffee, to take a bio break and come back. I hope everybody is fine with it. And so see you at 3:20 Chicago time. Thank you. But I will resume recording now. Very sorry for this. And but I have a question, and that's again something I could have asked also more people, but you mentioned it directly, like that you are working with cells. So I think you are going also for high performance computing for your models, right? To calculate and make predictions. So you are really so what is your strategy, to use Aurora or to use edge computing?
Yeah, so now we are using carbon at CNM. Is that also a supercomputer, right?
Okay.
So there are basically
smaller.
So because the workflow, Logan started a little bit, but we haven't really tested out the workflow between us and also supercomputer. So, but the vision is there are two possibilities that we can utilize the power of supercomputer. The first one is we want to incorporate simulation on the fly to make a decision, to help us to make a decision, especially in the generative model part. So the generative model will have a material generated and then goes through the simulation, then to do the ranking, right, whether it's suitable for the self-driving app to produce or not. So in this way, the simulation basically provides the feedback and also gave a score on the fly. And the other one is basically before we start the self-driving lab producing. So we want to use before or after. It's kind of a separate cycle. So for that one, so we want the supercomputer to help us to extract the physical features of our materials, either morphology or like property, so that we can
build a physical informed model for supporting the generative model to do a better prediction and also generation. Yeah.
So this was something I was curious about. So that's something, so just repeat that I understood you correctly. For the predictive modeling, you use the supercomputer. For just giving instruction fast decision, you use more the smaller computer on the side, because then you have a kind of algorithm already, right? So what you are just using. But do you also try to feed the supercomputer with new data on the flight, that the supercomputer in parallel could give you a better model and feed it back to the local computer?
No, we haven't tried that, but that's a good point. So now we basically use the supercomputer to extract, to simulate, to do the simulation and gain the feature.
Yeah. Okay. Thank you. You're muted, John.
Hi, this is Carol Thompson. So I'm not expert in polymers and I don't do this kind of work, but I'm looking at this as sort of a so this was put together mostly for polymers that would be used in electronic devices. So if I were someone submitting a proposal to the CNM wanting to use this, and I know polymers are a humongous field in different areas, what areas would not be served by this polymer automatic device?
Yeah, so Polybot is not designed for polymer. It's just because we are good at making polymer. So that's why we use polymer as a test bed to test out our entire workflow. We do have users who are working on inorganic material synthesis, for example, zinc oxide phase diagram like generation. So, and also some people working on gold nanoparticle synthesis and also perovskite material as well. So Polybots, because the workflow, they definitely have similarities among different research projects. So you can always look at our library of existing workflow, then to pick the one that looks most similar to your workflow, then we can do refinement, then we can make that to be suitable for different applications. So basically it's not just for polymer, it can be for another different material system as well.
Okay, Uta, quick. You're muted.
It's a quick question. It just crossed my mind about like having users, because we had another speaker yesterday talking about equity and giving also other people opportunities to use high-end instrumentation. So is a Polybot really available for universities that they could apply for beam time and say like, we would like to book it for a series of experiments?
Mm-hmm. Yeah, so Polybot is now already a user facility here. It's already a user tool here. We have several user proposals allocated already. So for APS, for the beam time, it has to go through the beam APS, right? That's another different, it's another system.
Okay,
Thank you. Okay, thank you very much, Ji. So we have one last talk this afternoon. That's Rajiv Asari from Material Science Division here at Argonne. Rajiv is a computational chemist, very interested in electrolyte design, and I'm guessing that's what he's going to tell us about today. He's also been pretty heavily engaged in seed projects here on autonomous discovery and self-driving laboratories. So, Rajiv, you have the floor.
Thank you, John. I hope you can see the slides and hear me very well.
You're good.
Yes.
Okay, great. So now, last talk. I'm very happy to be here, and I am the recorded personnel in this session. So you know the title now. It's going to be completely computational in nature. So these are the folks who contribute to the science I'm going to discuss. There are a few postdocs and a couple of staff scientists here, and some senior folks here guiding our efforts. So this is the one slide I just made it after yesterday's talk from Benji and others. So what I see here is we can do both autonomous experiments and autonomous simulations. One thing what autonomous simulations could do is you can look at much more a bigger space. Just for example, let's say if you have a billion combination possible, one would wonder why you looking at a 1 billion combinations. Autonomous simulations can be the a kind of principal component analysis method of the autonomous experimentations. And also similarly, you can call from an autonomous experiment, go and find this property for a particular material or satisfy a property based on certain combinations. You can always call as an agent for an autonomous simulation. So this could be, it could go hand in hand with the autonomous experimentations. And also quite a lot of progress happened within the last 2 months, especially the large language models and chat GPTs, transformers, and quite a lot of literature. So this literature data can be easily abstracted into the autonomous simulations, much easier than fitting into the on-the-fly experiments. So hopefully that will result into a discovery, and this iterative process can be continued. In this context, my question is, what are optimal materials? It's entirely subjective statement, because the optimal materials for electrolytes is completely different from the catalyst. So it depends on the questions we asked. We can say the optimal materials are designed to provide the best performance for a given applications. So in this talk, I would like to mention 2 examples. One is a molecules based one, and another is a materials based ones. Molecules are could be it's for energy storage. In particular, here I have 2 examples. One in electrolytes as a flow battery, and another one is a liquid organic hydrogen carrier. In the materials case, I have 2 examples shown, but I hope to show at least one, in particularly on the catalyst. So in the computational world, it would be most important in terms of prediction power is the quantum mechanics approach. We can compute the wave functions based approach or density based approaches to get model systems or fiducial systems very well in terms of nanometer length scale and also picoseconds. But this is very, very small. So we have to start from there, but having the feeling that it has to be connected with the multi-fidelity models like a molecular dynamics or a Monte Carlo or phase field approaches to make a realistic models. And this multi-scale model, often it's very difficult to bridge. So machine learning approaches or data science approaches could be one of the best way to bridge this gap between this quantum mechanics and, for example, molecular dynamics or molecular dynamics with a mesoscale model, etc. So in the outline, I mentioned I have a couple of examples I would like to show. One is a flow battery examples, another is a liquid hydrogen carrier example, and hopefully and a material example of a catalyst. I'll come back to this one by one. So one case, just want to show how to discover optimal molecules for flow battery systems. So if you don't know flow battery systems, we are trying to go beyond lithium-ion batteries. Here, simple example is if you take 2 tanks of materials, one tank has a anode equivalent, a molecule undergo reduction, and the another is a cathode equivalent, which is a molecule undergo oxidation. If you can put it together, one undergo oxidation, one undergo reduction, this difference in free energy can be converted to a potential using an Nernst equation. So this can be used as a in the power in a energy storage systems. This is more for a grid storage. The benefit of this one, it can be organic material, so it should be generally cheaper. And also it's highly scalable. It depends on the size of the tank. So you can put a large tank in the middle of somewhere far away, and you can pump it to a desired location to make this happen. So as long as it's flow, we can have this flow systems, and it's highly scalable in nature. On the right hand side, you can see a bunch of molecules. In one is more a negative side, another is on the positive side. You can see around 10-15 molecules is developed over the period of 10-15 years. So theoretically, you can make two molecules from extreme left and extreme right to make -2 and +2 around 4-volt batteries. Or in fact, we have some success in making 3.2-volt organic batteries during this R&D phase at Argonne. So, but we have to ask questions. It's like, what are these optimal properties, and how can we make better molecules with a little bit more interesting properties such as stability and solubility, and co-design certain properties, etc. So, for example, optimal properties often for this molecule is their reduction potentials or oxidation potentials. The higher the oxidation potentials and lower the reduction potentials, they have higher energy density. Luckily, simulations in particular DFTs are quite good at predicting these properties within 0.15-volt accuracy, especially for non-aqueous systems. Solubility is a tough problem, but you can predict quite a lot of solvation energy properties of these materials in a given organic solvents. And stability, in majority of these molecules undergoes oxidation reduction, becomes anions and cations. They have varying degrees of reactivity with external factors such as solvents or electrodes, or some other counter ions or other impurities. So the DFT can really, or simulations can really help on the fly understanding of certain reactivities, and also now increasing methods are available to predict some sort of synthesizability and sustainability scores or toxicity scores, so that we have some sort of confidence these predictions or these molecules you come up with are not toxic or possible to scale up. So so here, so one of the question I just want to answer here is how to discover optimal redoxmer satisfy multiple properties from a reasonably large chemical space much faster. So here the approach we used is Bayesian optimization. I think one of the previous speaker mentioned about the Gaussian process regression. I think that is the approach we used. This is a published work, so I'm not going to go detail into the approaches. But here we try to maximize three properties at the same time. So it's a multi-objective optimization. So in this case, this molecule is analyte. That means it undergoes a reduction. So three properties we took care of here at the moment is one is reduction potentials, a potential at which the molecule undergo electron attachment, and also a G-sol, which is a solvation free energy of this molecule in an acetonitrile. The more negative the number, that means the molecule has much more favorable interactions with the solvents around it. Lambda absorption is the proxy we used it for fluorescence. That because it's the molecule exhibit different color or a fluorescence at different state of charge, so it's easy to understand the health of a system. So we first we did some computational experiments. This is around 1,400 experiments, computational experiments. So you can see three histograms. Just let me explain one. There is on the right top, it's a reduction potential of 1,400 molecules in the solvation in the acetonitrile. So you can see it varies from 1.6 to 3.2. 3.2. So we want it's a little bit lower side, like 1.5, 1.7. That means you will get a little bit more energy density. The solvation energy on the bottom left is the more negative. It's better. So based on this understanding of certain structures, and also from a previous experiment, we know that it's 375 nanometer wavelength, and UV absorption is it's a reasonably good estimate for having some fluorescent properties for this particular core structures. It's not always true for materials, so it has to be tuned by and expert knowledge. So so this is the true data set, or we can consider this as a data set of 1400 experiments. So now let's quickly explain what is multi-objective optimization is. Here, as I mentioned, we used a Gaussian process regression. The key here, now we know 1400 molecules. Let's assume that we don't have that information. So we can start from a random 10 molecules. We can perform experiments. That is here it's a computation, 10 DFT computations. We can do we can make a Gaussian process regression based on this molecular representation. In particular, the molecular representation here is the molecules are smiles. If you bring a smile structure of a smile string structure of a molecule, you can convert to certain features using any number of methods. For this one example is we used a software called RDKit to make various features. In particular, here is 145 features. For example, number of carbon atoms, number of fused rings, etc. We can also convert this feature into principal components. For example, on the right-hand side, I mentioned that it's 22 PC. That means 22 principal components. But the point here is you can explain, you can make a machine learning model using these properties or the features or these principal components. You can use a Gaussian process regression. Since we have three properties, it is now going to be a three-dimensional space, and each property we can develop a acquisition function, which is a way we can improve this, improve the prediction when we include another point from the data set. So in this case, the selection of acquisition function is slightly tricky because now we have three properties. So we use the acquisition function space of these three properties. So the Pareto front is the compromise of the acquisition function of those three properties. So we can select the next one from the Pareto front. You can put it into the 11th experiment. So it can keep on going to find the molecule with these three desired properties. So it can be improved to 4 or 5 or 6 properties. It's going to be a little bit more tedious, but for thousands of molecules, it's easy to do this Bayesian optimization for the Gaussian process regression. So just for example, on the top left, on the left figure, you can see on the hypervolume with the number of evaluations diagram. You can see if you pick one molecule at a time from this 1400, it's going to take quite a lot of experiments to make this Pareto optimal molecules. Since we have this 1400 data set, we know that there is 22 molecules are Pareto optimal molecules, which is shown in the figure on the left with blue stars. So, but if you use a Bayesian optimization, you can get this 22 molecules within 120 DFT calculations. That means we can have a significant boost of identifying these molecules using this Bayesian type of approaches. So it's great to demonstrate on 1400, but the real value comes in here is let's say if you start building a data set of a 1 million data molecule, here on the right hand side, the points on red are marked with the unseen 1 million data set. So we managed to use the similar approach to come up with the 16 more new molecules coming from this 1 million new data set. I think this is the power of Bayesian optimization for coming up with a molecule with the three properties. This particular three properties. I think okay, now it's a negative side of it. So we used for three, we asked for three properties. Now we got three properties maximized of three properties, and we got some structures which is unsynthesizable. So if you look at it, three new molecules with the better properties, but their synthesizability is really, really bad. I think this is something we started addressing as can we come up with new molecules along with this one with a synthesis-driven rules-based approach using some sort of molecular generation. I think which is not part of this paper, but we have that approach now submitted to another paper. But the point here is we can start including this synthesis aware approach very early on, rather than relying on simple matrices like synthesizability matrix, and we can come up with some very interesting molecules with exciting exciting properties. So there is opportunities for improving this this multi-objective optimizations through the synthesis scoring. So I just want to put second point is very similar to this one. Here the point, the discovery is still a molecular discovery problem, but a slightly different aspects. We are trying to do a liquid organic hydrogen carrier molecule, just very similar to benzene or cyclohexane. This is a picture from Chiyoda Corporation. They officially used like large tankers from carrying these molecules from one place, from Japan to another place, to use this reversible hydrogenation and dehydrogenation mechanisms for this hydrogen storage applications. So the question here is, can we come up with the new molecules from extremely large chemical space? So it's not like a 1 million molecule we can do multi-objective optimization. I'm talking about billions of molecules. Can we do this one? I think that is the promise of these projects. We started looking at it, but here also we have to look at optimal properties of liquid organic hydrogen carrier. And also I have to, I think one of the previous speaker mentioned Gaussian process regression is every time when you do a GP, you have to do covariance of the metrics. That's you cannot do on 1 billion molecules. I think you have to come up with some GPU-based approaches or deep learning approaches. So in this particular example, I'm just trying to find out optimal molecules with a desired enthalpy, which is based on some studies. We identified 40 to 70 kilojoules is a good enthalpy, and luckily DFT is a good DFT is good enough approach to compute enthalpies. And also there are chemoinformatics based approaches. We can identify high hydrogen content, easy to catalyzed, or a non-toxicity, a non-food item, etc. So we can compute this one. I'm going to skip this one for the sake of it. Just simple example here is we looked at the literature. We found out there are around 30 molecules we know that reasonably explored as a hydrogen storage materials, but there are chemical space people often talk about 166 billion, which is a GDB 17 molecules, means 17 heavy atoms, and the rest of them are hydrogen. There are 166 billion molecules. So there is a one website in Switzerland, one professor accumulated this synthetical approaches, the graph-based approach to enumerate 166 billion molecules. I think Ian Foster, our collaborator, he managed to dig this data for 166 billion molecule to Globus. So we used 166 billion to begin with. I think Logan Ward did a lot of sweating on Theta, the supercomputer at Argonne. So we come up with we have looked at this data set. We have around 30 molecules, which is the experimental available material. So we used a similarity of 166 billion with the 30 molecules to come up with a similarity index. And also we during the process, during this 2 years of this project, we developed some criteria called a scoring criteria, come up with the two postdocs, Hassan Harb and Sarah. We come up with this criteria. They reduced this 1 million to 3,000. Then we did a 3,000 DFT calculations, come up with a few exciting new molecules, which is about to be submitted into a nice paper. But the point here is even with a simple approximation of identifying existing trends within the molecule, we can come up with a dehydrogenation index trend from here, and we can come up with the new molecules, which can be predicted within a fraction of a second. So some of the promising new molecules I'm shown on extreme right. You can see some of the molecules we haven't even thought about exist, and they have extremely compatible enthalpies. The only problem we have tested on the kinetics of these things, and which is underway at the moment. Let me quickly show one example on the solids. So two examples I've shown is on molecules. Now, just one more thing on solids. Here it's a heterogeneous catalyst. We are trying to reduce oxygen, try to remove oxygen from biomass molecules, so that we can make use of these biomass molecules to jet fuels or sustainable aviation fuels. I think one of the processes is removing oxygen from it. So this one, you can see the question here is majority of the time when you try to remove oxygen, this oxygen binds on the catalyst, and the catalyst get oxygen. It changes the phases of the catalyst. For example, moly-carbide become moly-oxy-carbide. For something like that one. I think the best catalyst is known for this kind of activity is a platinum, which is beyond the cost of this. It's beyond the cost of these approaches. So that's a reason for this for our effort. For example, here we ask the question: how to perform cost-efficient estimation of crucial descriptors for a heterogeneous catalyst faster. So the answer here is we try to use a data-driven approach. For example, oxygen binding energies using a DFT, and from that one we developed a graph neural network approach. Here, just for example, based on if you look at the middle figure here, if you look at benzene or any other organic molecule with oxygen on it, if you attach to the surface, the oxygen get trapped into this top surface, and it causes the phase transformation of the surface. So if you can remove very efficiently oxygen by adding hydrogen, it will remove as an water. Then the catalyst surface could get regenerated. But majority of the time, the oxygen will bind strongly. So that we need a catalyst who can bind oxygen less strongly. Meantime, they can also bind. You can remove the oxygen from the surface from the molecule. So to the extent of finding catalyst, so one catalyst we found based on our catalyst cost analysis from Bioenergy Technology Office. This is an applied project. That's why cost is very, very important. So we found out molybdenum carbide is a decent catalyst. We can utilize this catalyst for biomass conversion reactions. So we used the moly-carbide as our platform to build a new catalyst, and Hugh Dover, and he is instrumental to develop this project. What he did is he used almost all the possible dopants on the from the periodic table, and also almost all the catalyst facets of this of the catalyst moly-carbide. You can see that in MO2C is not like a typical palladium 111 or catalyst. It's already have a MO2C. That means it's already have two species. It's orthorhombic shape and also orthorhombic in nature, and also they have various surface facets. And when we include oxygen, then it's become when we include the dopant, it's become kind of a high entropy alloy itself. So it's not that easy to figure it out. So our approach was to develop some data first. So here Hugh did a 20,000 vast periodic DFT calculations on supercomputer called Theta. It took around 20 million CPU allocations. So what we used that data as the data for the oxygen binding energies. But for the development of a machine learning model, what we used is an unoptimized absorption geometry, not an optimized structure. So all you need to provide is a graph of the binding structure. You produce the binding free energy of oxygen. So that we can understand binding free energy of any given site of any type of this this catalyst. So we can build Wolf constructions if you want to find the optimal binding energies of any given surface. Just an example, especially on the right hand side, if you look at it, there is a parity plot. This gives if you use around 20,000 data sets, if you build a nice machine learning model or some graph neural network, it's only take a few seconds to predict binding energies within. It's not a great accuracy, 0.176 EV. It can be improved, But given this catalysts are not simple palladium 111, this is a little bit more complicated catalyst. So maybe 20,000 is not sufficient enough, but DFT accuracy itself a 0.2 volt for this system. So with a sufficient confidence, I can say that this is still a decent catalyst model. I don't know. I think I'm running out of time. So this catalyst model, and not only just predicting the active site, binding free energies or binding energies, we can also, from this machine learning model, you can do some feature importance. For example, on the right side, it's called some saliency plots. So if you do derivatives, you can identify effect of a species. For example, if you have a tantalum, we kind of know that it's a tantalum going to bind oxygen very strongly. Meantime, if you have a cobalt, it bind less strong. So it is not only showing a regression number, but also showing some sort of chemistry physics behind a feature importance. So the graph neural networks for the catalyst, it's working very well. That's the point I was trying to make. So in summary, so I just want to reiterate the fact that when two molecular discovery projects are it's published, so the GitHubs are available. You can see this is the Bayesian optimization. This is the, I know this is the 1 year, 2 months is still a very big time in AI world, but we are trying to improve this one using some sort of a deep kernel learning so that the accuracy can be improved further. On the catalyst paper we published recently on digital discovery, that catalyst efforts, one of the bottleneck is it has to have quite a lot of data. The active learning approach can be also used in there. I think we are looking at it. And although we are excited about this informatics based approach for a very large scale screening for liquid organic hydrogen carrier. But the challenges remains, I think, properties like kinetics is very important, and the catalysis of reversible hydrogenation is also very important. So in summary, I can say, AI enabled material discovery has some future, and it can be a good help for autonomous experiment developments. Thank you.
Okay, thank you, Rajiv. That was quite a tour of some very interesting, of 166 billion molecules. That's impressive. So,
yeah, we are the first people to do it. I think that is the beauty.
Okay, the floor is open for questions. Okay, so I'll ask one. So, forgive me if this is a naive view of this, but what I'm seeing here, it looks to me like what I would call kind of forward modeling kind of approach. So you want to optimize some kind of parameter, and so you go to some catalog of well, billions of molecules, and then you do some screening calculations and various other things to eventually filter it down to some manageable number. Is there any role for like inverse design though in this space where you have some targeted property and then you actually try to design some molecule that might be the 166 billion and 1th that isn't in the box to start from?
Yes, yeah, you're absolutely right. I think there is a few generative modeling approaches can be used for this one. I think we have colleagues using it. I think we try to not replicate the same thing. I think that's one of the reasons we just have moved away from inverse design. And if you can see from the first one, we are trying to develop a data around certain molecules because we know that we have synthetic experts who can make those molecules. So we carefully curate it within the region. I think that's what experimentalists will do it because we cannot build an autonomous experimentation with 166 billion molecule creation, right? So we even I think you remember the Marty Burke's experiment Benji mentioned. I think they have a 25 reagents sitting there, so they can mix and match and make whatever the molecule. within this 25 batches of reagents, right? So similarly, so the inverse design, it's easy to do inverse design now because you can ask ChatGPT, it will come up with a new molecule for sure. I think there's a nice paper from EPFL about creating new molecules from using ChatGPT. You can come up with a new molecule, but this molecule has also a similar problem like what we mentioned in the Bayesian one, synthesizability. So it has to be connected with a synthesizable situation. So synthesizable situation, the inverse design there, it's you need to find out what reagent you have already in stock and what are the optimal conditions to make certain molecules you thinking about it. So we cannot go beyond that space. I think we can explore billions of molecules, but it comes to a phase space or discrete space for autonomous experiments, we may have to do very careful down selection.
Of course, yeah, no, as many speakers in this workshop have pointed out, the synthesizability problem is, is really should be at the top of the pyramid, right? So, yeah. but thank you. Okay, Uta, looks like you may have a question or a comment.
Yeah, it was for like, so the synthesis, that's really something that's bugging me also a lot, right? Because prediction, like AI, or no, yeah, AI, but also like the big machines, they can suggest 30,000 possible structures and what we could try out and per day, and then it's something like, okay, but most of them we cannot synthesize, right? How far are we actually away that we have also opportunities to really simulate complete synthesis routes? Do you have an idea for it or a feeling for it? Because this would be a big game changer for us, right?
Yeah, for organic molecules, we already have a template-based approach. Any given molecule, you can have some retrosynthetic approaches available. Inorganic, I think one of the speakers mentioned, inorganic can be synthetic approaches, but it's cooking condition dependent, right? There is quite a lot of uncertainties, so there is I think Gerd Cedar from UC Berkeley would be the best person to answer it. I think there is some synthesizability scores available for based on free energy. I think Chris Wolverton has something from Northwestern. So they're basing on free energy. I mean, there is kinetic traps. There is kinetic traps, and which is a trap for the theoreticians too. So,
yes. There is. So my dream would be like if you really understand like complete routes with intermediates, right? Because I mean, my beamlines are very good in situ synthesis. So that's one of our sports here. But if you really could predict the intermediate states and really could simulate further, right? I mean, this is gigantic what you need to do. But this would open up a complete new world in what you could predict, because it's going beyond this, right? Because sometimes you need steps in between to get to your final product.
Yes, I completely agree. I think this is one of the reason I was thinking about the autonomous simulations, because since the computation is getting bigger and bigger, we can keep on putting molecules and make more data and data. I think this is going to help.
Yeah, that's also something I've learned recently, is that experiments are also sometimes virtual experiments. So simulations can be experiments, right?
That's right. Yeah, I started using that computational experiments very recently after somebody from an experiment say, why don't you use computational experiment? Much more fancy.
Yes.
Yeah, sure. Why not? Yeah.
Any other comments or questions for Rajiv?
I think we really should come to an end here. We are past the time significantly by 10 minutes already. So just to close the workshop, I think it was, for me, something I enjoyed a lot. I believe I've learned a lot, like what the state of the art is. I understand like that for just quality improvement and so on, there's a lot of things established already, right? And this is also easy to to optimize the beamlines nowadays, where I would say like we are not far away from a brave new world where we are getting better in ensuring that we are on top of the optimized alignment of our systems. Discovery is more challenging, but the first step is really to get to the automation and learning how to optimize everything. I think then the next step is not far away. I discussed it with John, so I think we agree on this point. John, you also would like to add something?
No, I think you pretty much summarized it all. There was a terrific workshop. I want to thank all the speakers, those that are here and those who have gone on to other things. Appreciate their time and energy and contribution. So
yeah,
that we probably can call it a wrap. What do you think, Uta?
Yeah, thank you. Thank you very much. And yeah, thank you for being here. And it's time to say good night and good afternoon for everybody.
Thank you to everyone for attending.
Yeah.
Have a good evening.
Thank you.
Bye.
Bye.